Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and today I'm going to go over another daily math problem. This is the last one I posted on on the Facebook group Classical Mathematics. Yeah, and this one involves what I'm calling stars here. I have three pictures of them. They're kind of faint. I don't know if you can see this, but anyway, let's begin. So here, first I have to define the problem, state the problem as always. So here's the statement of the problem. So we say, first of all, we say that for arbitrary positive coprime integers n and m, that just means there's no common divisor of n and m. And we also require that 2m is less than n. In other words, m is less than half of n. And now I'm going to find the star capital S of n comma m. This is going to be a star, an endpointed star, a particular endpointed star. It turns out there's a total of m, the um, floor of m over n over 2 possibilities. M can be anything from 1 to the floor of n over 2. So, for instance, the star I show here is S7 comma 3. And I define it by the line segments that make it up. So, yeah, the line segments are points on the unit circle. I'm not going to read them all off here, but they involve sines and cosines in their x and y coordinates. That's just kind of a fancy way of saying that the vertices lie on a regular n-gon, with one of its vertices at the top of the unit circle. And then you go around, I guess, the total of m over n of the way around the circle. In other words, 2 pi m over n. If you prefer degrees, 360 times m over n degrees. So for this particular example, this star has 7 vertices. You would go around, you'd start at the top vertex and you'd go around 3/7 of the way. That takes you to the bottom right vertex, and then you just keep going like that. You keep going around 3/7 of the way clockwise until you complete the star. That's just a fancy way of saying this. So that's the definition of Sn comma m. And I haven't told you what the problem says yet. So the problem is the problem asks for the number of self-intersection points of Sn comma m. And in this case, for S7 comma 3, you can just count them, and I think you can see there's 14. There's two small. If you like, there's a smaller star inside this big one, and the smaller star turns out to be a smaller version of S7 comma 2. And I think it's pretty easy to see that that smaller star has a total of 14 vertices. Those are the 14 intersection points. Notice that they lie on two different circles of two different radii. The one with a bigger radius has 7, and the one with a smaller radius also has 7. So there's a total of 14. But that's just for a particular example. We want a general formula that works for every pair S comma n, where n and m are coprime and 2m is less than n. So how do we solve this problem? Well, as usual, I first simulated this on Mathematica. This did not solve the problem. I'm just showing you some examples. I wrote some Mathematica code. This first line of code is really just a Mathematica, one-line Mathematica function for generating a Sn comma m using the same coordinates that I gave in the problem, just involving sines and cosines. And you can see I've showed 3 of them here. The top one is a familiar pentagram or 5-pointed star. That's S5 comma 2, which I'm sure you guys are all familiar with. They're on the American flag, 50 of them on every American flag. So I think everybody's familiar with a pentagram. And then the one in the bottom left corner here is S7 comma 2. And then the one on the bottom right, this is the one I showed in the previous slide. That's S7 comma 3. So I think you kind of know what these things look like. But, using Mathematica, you cannot solve this problem for general income. In general, you can't solve a problem on the computer for general values of the parameters you're given. You have to do some analysis for that. So anyway, here's my analysis. So here's how to solve this problem. So what we want to do here, if you look at this diagram on the bottom, this is S8 comma 3, and I don't know if you can see this, but one of these line segments, as a matter of fact, the first one in the construction, the one that goes from the top vertex to the one 3 vertices over going counterclockwise, that one's shown in red. And what we're supposed to do here, we're not counting all the intersection points. We're starting by considering one line segment of the star. And there's always a total of n. So in this case, there's a total of 8 line segments that make up S8 comma 3. And what we first want to do is we want to count the number of intersection points along that line segment. And the total number is going to be, in this case, 8 times that. Well, you have to divide by 2 at the end because, well, anyway, let me continue. So the first thing you should notice is that if you just look at the shorter circular arc between this red line segment, that goes 3/8 of the way around. In general, it's going to go a total of m over n of the way around the circle. And I think you can also see that there's going to be, in general, m minus 1 vertices along that shorter arc between the red lines, shown in this case just 2. I mean, there's a total of 3 vertices if you count them starting from, if you don't count the left vertex of this red line segment, if you're just counting the number that go to the right vertex of the line segment, you go 1, 2, 3, and then you end up at the right vertex. But we're not counting any vertices on the line segment. There are exactly 2 that are strictly between the the 2 vertices at the ends of the red line segment. And notice that for each of these 2 vertices, that intersects this red line segment exactly twice. Every vertex of Sn comma m, for every value of m and n, is always going to have 2 line segments coming out of it. And those 2 line segments are going to intersect any other line segment. So in particular, each of these 2 vertices intersects this red line segment twice. So there's going to be a total of 4 intersection points along this line segment. In general, there's going to be a total of 2m minus 2 because it's m minus 1. Is that right? Yeah, there's m minus 1 coming out of each of the m minus 1 vertices. There's m minus 1 vertices between the 2 vertices making up the edge of the line segment, and then for each of those vertices, there's 2 line segments coming out. So there's a total of 2 times m minus 1, or if you like, 2m minus 2. But now there's also 8, in this case, 8 line segments. In general, it's going to be n line segments. So the total number of intersection points was going to be n times 2m minus 2, but we still have to divide by 2. And the reason we have to do that is because every vertex is shared by 2 line segments. So we're overcounting. If we counted every line segment, we're counting every intersection point twice because every intersection point belongs to exactly 2 line segments. So in the end, you have to divide the final result by 2. So that's going to give n times 2m minus 2 all over 2, which is equal to n times m minus 1. So that's a general formula. The number of intersection points of Sn comma m is n times n minus 1. That's kind of a nice formula. In this case, since n is 8 and m is 3, we're going to get 8 times 2, or 16. And I think you can see if you count the intersection points in the middle, there are indeed 16 intersection points. Each of them lie along regular octagons. There's 8 that make up the smaller regular octagon, and another 8 that make up the bigger one, just like there was for the regular heptagon, the other example. For that one, there were 14, but for this one, there's 16. And I think I should point out that these numbers can get really large. I mean, here's an example. Here's S100 comma 49. And this kind of looks like almost like an optical illusion or something. It's one of those things that you can look at that can kind of hypnotize you a little bit. I don't think you can even see all the intersection points in this one, but this is an S100 comma 49. So this is a 100-pointed star where you're going almost halfway around each time. And that gives you a total of 4,800 intersection points, and you can't even see most of them. Anyway, so these can get really large, these numbers. But I think this is kind of a nice problem, and I think it's pretty simple once you understand what's going on. So anyway, that concludes my video for today on counting intersection points of stars. Thank you for watching. Long live math, and I'll see you guys next time. Bye.